Hey, my name's Andy McBride. I'm an embedded flight software engineer at Lockheed Martin Space, and today I'll be discussing the payload flight software for a 3U CubeSat that's being developed at Lockheed Martin for a program called Jument. So the agenda for the presentation is to first go over an overview of what Jument is, and then I'll be talking more specifically about a 3U mission, the 3U flight software, a specific machine learning application that was developed for this demonstration, and then the strategic value for Lockheed Martin Space. So Jument is a series of CubeSat projects beginning with a 3U, which is planned to launch later this year, then moving on to two 6Us later next year, and a 1.5U, which is planned to launch at some point that we don't know yet. So these projects are meant to host bleeding-edge Lockheed Martin technologies that have yet to fly on any mission, and the goal for the Jument CubeSats is to develop them quickly and with low cost, which enables us to demonstrate some of these new technologies long before they're planned for any usage on an actual mission. By leveraging a simple CubeSat project, we eliminate a lot of the cost and the risk that's associated with sending something to space. So this means that we're able to increase the technology readiness level before we start developing it for a higher class mission. So when you're developing something for a higher class mission, you usually have a lot more rigor involved. So that means a lot more testing and qualification. So if you're able to use a CubeSat demo to host that technology and actually prove it out in space, that's going to save you a lot of time and money. So one of the ways that we found that we could do this is to host our payload or our new technology on an existing CubeSat project or an existing university STEM project. So for the 3U CubeSats, that's exactly what we did. We found that the University of California had already designed and built a CubeSat, and they have heritage operating CubeSats and ground station equipment. So we decided to work with them and develop our own payload. And for the 3U, we designed a payload that has two optical elements, a infrared camera and a visible light camera. And we're also flying an NVIDIA TX2i single board computer that's used for controlling the payload operations. Last summer, we also brought in several interns from the Colorado School of Mines. They helped develop some AI/ML algorithms for automatic target recognition, and they helped write the payload software in general. They wrote some of the camera controller applications and some of the bus interface apps. So throughout the rest of the presentation, I'll be specifically focused on the 3U since that's the most developed so far, and it's going to be the first one to launch in the series of Jument CubeSats. For the flight software on the 3U, we plan to host Lockheed Martin SmartSat, which is a Lockheed Martin internally developed software infrastructure, middleware, and set of lower-level drivers, which creates a modular and open software architecture. SmartSat enables more rapid development of software and payload applications in this case. Kind of makes it easier for us to integrate with the bus right out of the box, and it also has an existing ground side that could be leveraged for interpreting mission data on the ground. So now we'll look at the concept of operations for the Jument 3U CubeSat. The 3U is slated for a December 2021 launch into a sun-synchronous orbit at 550 kilometers. After approximately 30 minutes, the CubeSat is going to power on and will begin pointing its solar panels at the sun. At that point, we're going to wait to establish a link with one of the two ground stations located at either Lockheed Martin or at USC. After communication's been established, we will uplink a relative time sequence command script that could be used to begin nominal operations of the CubeSat. So this includes pointing towards the Earth, collecting infrared and visible light images, and performing machine learning algorithms on those images. Finally, after that, we'll begin waiting for a link with one of the two ground stations again, at which point we could downlink some of the collected imagery, either pre-processed or post-processed images, and then downlinking health and status information from each of the applications to make sure everything's working correctly. So throughout the duration of the mission, which is 180 days, our primary objective is to utilize the processing power of the NVIDIA TX2i and demonstrate the machine learning algorithms on those images. And I'll talk more about the specifics of what software we actually have on the TX2i now. So as I mentioned earlier, the payload flight software is written using Lockheed Martin SmartSat infrastructure. In this case, it's loaded with SmartSat's embedded Linux operating system. The load includes all of the core SmartSat applications used to handle common flight software solutions such as application and file management and publishing telemetry. We then have all of our mission-specific applications. This includes 2 camera controller apps, one for each of the optical payloads, the infrared camera, the visible light. These are controlled using some underlying USB libraries. Then we have our primary demo app called SuperRes, which uses machine learning to enhance the resolution of the visible light images that we collect. I'll talk more about this in a minute. We also have the bus interface app, which is used to send and receive data from USC's bus. So if you want to uplink a command and change the behavior of something on the payload, like tell it to take an image, you have to do that through the bus interface. The full stack also harnesses the core SmartSat services such as inter-application messaging, and which is used to handle and process data, and then SmartSat's I/O service, which is used to handle peripheral interfaces. The full stack then leverages the power of the NVIDIA Jetson TX2i. It's built on top of the CUDA-X software stack, and it's supported by the NVIDIA Jetpack SDK. On top of that, we're also using Lockheed Martin's internally developed SmartSat SDK, which is used to write SmartSat applications. SmartSat provides a nice software development kit for each platform that it supports. So when we go to SmartSat and they start supporting the NVIDIA TX2i, they provide the developers with an SDK that they could use to quickly start writing applications, which really enables rapid development, which is one of the main focuses of the Jument program. So now I'll talk more about what the SuperRes application is specifically doing. So SuperRes is the main focus of the 3U mission because it will be demonstrating machine learning on the CUDA-capable stack of the NVIDIA TX2i. The machine learning algorithm uses a network that's trained off of high-resolution imagery, and then it devises weights that could be used and applied to low-resolution imagery to enhance the resolution overall. So the neural network allows for gains of 2x, 4x, and up to 8x image quality or resolution. So when you increase the resolution, you're also increasing the image size, which you have to keep in mind. So at the bottom of the screen, you can see the low resolution input to SuperRes, which is a picture of a parking lot if you can't tell. And after it goes through SuperRes, the image is 4 times as big, but it has twice as good resolution. So kind of the goal behind this is you might have some other desirable onboard spacecraft algorithms such as automatic target recognition, and if you're able to do some pre-processing before sending your image into target recognition, by increasing the resolution, you might have more success with the ATR automatic target recognition algorithm. Another added benefit is that for low-cost optical equipment, or maybe lower swap, smaller cameras and lenses, or lower mass, you could get the same results out of it if you run it through the SuperRes application. So if you don't have the space to put like a fancy, expensive camera on your small CubeSat, if you put SuperRes on board, you can increase the resolution, so it's almost like you have just as nice a camera and lens in the end. This demo is also going to show how SmartSat's helping enable complex mission solutions on orbit, which are oftentimes run on the ground. So by running this algorithm in space, you have all the pre-processing required to detect a target, but without all the complexities of potentially transferring data back and forth from the ground. Finally, we'll talk about the strategic value that this adds for Lockheed Martin Space. So this will be one of the first missions that's hosting Lockheed Martin SmartSat. So it'll really help to prove out some of the features that make SmartSat what it is. So SmartSat was intended for multi-mission capability and reconfiguration. We could upload some different configurations for the applications after they've been running for a while, or we could upload a new app to show that we could do that. Since it's one of the first flights, it would be cool to do that after like 80 days if we're done with our super res demonstration and we decide that we want to utilize the infrared camera more. We could upload a new app that processes some of the infrared images. SmartSat also helps support rapid development of third-party applications, and that's something that we've already started to help prove out. We had the interns working last summer who were quickly able to get the SDK and start developing apps as soon as they got it. So this will also be one of the first flights proving out SmartSat ground, which will allow for easily collecting and processing data from the CubeSat. It also helps show cutting-edge computing using the NVIDIA TX2i. This is the first time Lockheed Martin has launched one of these single-board computers, and SmartSat was kind of built around the idea of enabling more complex solutions and algorithms in space. So by flying a more cutting-edge processor, we're going to be able to prove that on this mission. We also have our partnership with universities. So not only are we helping to inspire and train future engineers and prepare them for the workforce, we're kind of helping each other out in the fact that we'll be able to launch some new technologies hosted on those CubeSats. Hopefully in the future Jument series, we're also able to release the SmartSat SDK out to the universities so students could write their own third-party applications, and we could host those on the payload or potentially have them help us with bus flight software. Finally, this demonstrates the advanced imaging that's brought to you by the GPU on the TX2i. We will use the SuperRes application to test machine learning algorithms on board with SmartSat, and we'll potentially use some intern developed object detection algorithms that were developed last summer. So that's it for the 3U presentation. Thanks for listening, and definitely keep an eye out for more Jument stuff in December when we're planning to launch. And I'm sure you'll hear more about the 6U and the 1.5U in the future. Thanks.